In order to be good at algebraically factoring, I'm going to go back to the basics and first talk about factoring with numbers. Usually this topic is related to the prime factorization. There's a number of strategies for finding the prime factorization. Most people like to use a factor tree. Here's an example of a factor tree for 24. Often we'll write the result using exponents if there are repeated factors. And here's another example of the same tree. Notice how different strategies still give us the same answer, 2 to the third times 3. So the prime factorization of 24 is 2 to the third times 3. When you think about what factoring really means, you're really just taking an expression and writing it as a product. So 2 times 2 times 2 times 3, or 2 to the third times 3. Each of these 2's and the 3 we'd say are the factors of 24. So this process was factoring 24, when we turn 24 into an expression like this. There are 4 main techniques for factoring expressions. There's a technique called finding the greatest common factor. We'll learn the sum product rule. And a technique called splitting the middle. Let's start with the greatest common factor. Any expression, such as, let's say, 4x plus 12, that's made out of more than one term, so 4x and 12 are terms, can be factored possibly by the greatest common factor if the terms share a common factor other than 1. In this case, if I took the prime factorization of each of the terms, I'd have 2 times 2 times x and 2 times 2 times 3 for 12. Well, in common, 4x and 12 have 2 2's in common. 2 times 2 is 4, so I'm going to put those two 2's out here as 2 times 2, and then I'm left with x from the first term and 3 from the second term. And since there was a plus here, I'm going to add them. Notice how this expression, 4 times x plus 3, is still equal to 4x plus 12. 4 times x would give me 4x, plus 4 times 3 gives me 12. The factored form should start to look to you just like the factors of 24. Remember, 24 was 2 times 2 times 2 times 3, where it was all written as a multiplication problem. Well, now 4x plus 12, a problem that used to be addition, is written in terms of multiplication. 4 times x plus 3. Here's another expression that can be factored with the greatest common factor. Let's take the prime factorization of each term. So 2 times 3 times x times y. The first term, plus 3 times x for the second, plus 2 times 3 for the third. And find any factors they all have in common. So a 3, and that's it. Now, I'm going to put that 3 out in front and multiply the 3 by the rest of the expression. 2x squared y plus 3x plus 4. This expression has been factored because I factored out the greatest common factor from each of the terms. And now this value, 6x squared y plus 9x plus 12, is written as a product. There's multiplication. An extension of this type of factoring is called factoring by grouping. Let me show you how factoring by grouping works. Factoring by grouping involves expressions with 4 terms that can form 2 groups. In this case, if I were to split these 2 groups up and factor each group individually, from the first group, the common factor is just x. So I could factor out an x and express the first group as x plus 3. In the second group, the common factor is 6. So I could factor out a 6, and again I'm left with x plus 3. Well, now I have two terms again. Each of these terms is formed just by multiplication, right? 6 times x plus 3 and x times x plus 3. And in each of my terms, I have a common factor again, which is x plus 3. So I'm going to remove the x plus 3 from both of the terms, factor it out, and write it once right here. And I'm going to multiply it by what's left once I've taken it away. So if I remove it from there and remove it from there, now I need to multiply x plus 3 by x and by 6. So I do that like this. Actually, let's get the color right. Notice how this works, that if I take this x plus 3 and I distribute it, I have to multiply it by x and 6. That would mean x plus 3 times x plus x plus 3 times 6. This gives me x squared plus 3x right here, and 6x and 18 from right here.